Hello students, let's continue the chapter 13 probability. In this e-lecture, we will discuss about random variables and its probability distribution. A random variable is a real valued function whose domain is the sample space of a random experiment. In most of the random experiments, we were not only interested in the particular outcome that occurs, but rather in some number associated with that outcomes, as shown in the following examples. In tossing two dice, we may be interested in the sum of the numbers on the two dice. That may be 2, 3, 4, 5, 6, and so on. Maximum sum is 12. In tossing three coins, we may be interested in the number of heads, means no head, one head, two heads, three heads, that is 0, 1, 2 or 3. Let's consider the experiment of tossing a coin two times in succession. The sample space of the experiment is a set containing possible outcomes HH, HT, TH and TT. If X denotes the number of heads obtained, then X is a random variable and for each outcome its value is as given below. For HH, X equals to 2 as HH contains 2 heads. For HT, X equals to 1. For TH, X equals to 1 and for TT, X equals to 0 as TT contains no head. More than one random variables can be defined on the same sample space. For example, let Y denote the number of heads minus the number of tails for each outcome of the above sample space S. Now, HH means 2 heads and 0 tails. So Y equals to 2 minus 0 equals to 2. HT means 1 head and 1 tail. So Y equals to 1 minus 1 equals to 0. TH means 1 tail and 1 head. So Y equals to 1 minus 1 equals to 0. TT means 0 head and 2 tails. So Y equals to 0 minus 2 equals to minus 2. Thus, X and Y are two different random variables defined on the same sample space S. Let's discuss some more questions. An urn contains 5 red and 2 black balls. 2 balls are randomly drawn. Let X represent the number of black balls. What are the possible values of X? Is X a random variable? Here, given urn contains 5 red and 2 black balls. Let R represents red ball and B represents black ball. 2 balls are drawn randomly, hence the sample space of the experiment is a set S containing possible outcomes BB, BR, RB and RR. Let X represents the number of black balls. For outcome BB, X equals to 2 as both the balls are black. For BR, X equals to 1 as it contains 1 black ball. For RB, X equals to 1. For RR, X equals to 0 as it contains no black ball. Therefore, X is a function on sample space whose range is a set with elements 0, 1 and 2. Thus, X is a random variable which can take the values 0, 1 or 2. Next question. A person plays a game of tossing a coin thrice. For each head, he is given rupees 2 by the organizer of the game, and for each tail, he has to give rupees 1.50 to the organizer. Let X denote the amount gained or lost by the person. Show that X is a random variable and exhibit it as a function on the sample space of the experiment. Here, X is a number whose values are defined on the outcomes of a random experiment. Therefore, x is a random variable. Now, sample space of the experiment tossing a coin thrice is a set S containing 8 possible outcomes as shown. X equals to amount gained or lost by the person. For each head, person gets rupees 2. So for the outcome HHH, he gets rupees 6. So X equals to rupees 6. Next, as there are 2 heads and 1 tail in outcomes HHT, HTH and THH. So person gets rupees 4 and lost rupees 1.50. So X equals to 4 minus 1.50 equals to rupees 2.50. Next, as there are 1 head and 2 tails in outcomes HTT, THT and TTH. So person gets rupees 2 but he has to give rupees 3, means loss of rupee 1. So X equals to minus 1. For each tail he has to give rupees 1.50. So for outcome TTT he has to give rupees 4.50, means loss of rupees 4.50. So X equals to minus 4.50. Thus, for each element of the sample space, X takes a unique value. Hence, X is a function on the sample space whose range is a set with elements minus 4.50, minus 1, 2.50 and 6. Next, probability distribution of a random variable. The probability distribution of a random variable x is the system of numbers like x is x1, x2 and so on xn. Then corresponding probabilities of x is p1, p2 and so on pn, where each pi is greater than 0 and sum of all the probabilities, that is summation pi equals to 1, where I equals to 1, 2 and so on up to n. The real numbers x1, x2 and so on xn are the possible values of the random variable x, and pi is the probability of the random variable x taking the value xi. We also denote it as p capital X equals to xi equals to pi. Students, always remember that in the probability distribution of x, each probability pi is non-negative and the sum of all the probabilities is equals to 1. Let's discuss some examples. First, 2 cards are drawn successively with replacement from a well-shuffled deck of 52 cards. Find the probability distribution of the number of aces. The number of aces is a random variable. Let it be denoted by x. So clearly x can take the values 0, 1 or 2. Means no ace, exactly 1 ace or 2 aces. Now, since the draws are done with replacement, therefore the 2 draws form independent experiments. Now, Px equals to 0 equals to probability of no ace equals to probability of non-ace card in first draw multiply probability of non-ace card in second draw when first card is replaced before the second draw. This is equals to 48 by 52 multiply 48 by 52. After simplification, we get 144 by 169. Next, Px equals to 1. Probability of exactly 1 ace. Here, 2 cases arise. Case 1, first card drawn is ace and second non-ace. And case number 2, first card drawn is non-ace and second ace. So, Px equals to 1 equals to probability of A's and non-A's plus probability of non-A's and A's. This is equals to probability of A's multiply probability of non-A's plus probability of non-A's multiply probability of A's. As probability of A's card is 4 by 52 and probability of non-A's card is 48 by 52. So Px equals to 1 equals to 4 by 52 multiply 48 by 52 plus 48 by 52 multiply 4 by 52. After simplification, we get 24 by 169. Now, Px equals to 2 equals to probability of 2 aces. This is equals to probability of A's card in first draw multiply probability of A's card in second draw when first card is replaced before the second draw. This is equals to 4 by 52 multiply 4 by 52 equals to 1 by 169. Now we write the required probability distribution in the tabular form as shown. Take one more question. Let a pair of dice be thrown and the random variable x be the sum of the numbers that appear on the two dice. Find the probability distribution of x. The sample space of the experiment consists of 36 elementary events, or we can say possible outcomes. The random variable x is the sum of the numbers appearing on the two dice. It means minimum value of x is 2 and maximum value is 12. So x equals to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or 12. Now probability of x equals to 2 equals to 1 by 36 because 1 is the only favorable outcome for sum of the numbers equals to 2. Next, probability of x equals to 3 is 2 by 36 because 1, 2 and 2, 1 are two favorable outcomes for sum of numbers equals to 3. Next, probability of x equals to 4 equals to 3 by 36 because 1, 3, 2, 2 and 3, 1 are three favorable outcomes for sum of numbers equals to 4. Similarly, probability of x equals to 5 equals to 4 by 36 and probability of x equals to 6 equals to 5 by 36. As 1, 6, 2, 5, 3, 4, 4, 3, 5, 2 and 6, 1 are six favorable outcomes for sum of numbers equals to 7. So probability of x equals to 7 is 6 by 36. 2, 6, 3, 5, 4, 4, 5, 3, 6, 2 are five favorable outcomes for sum of numbers equals to 8. So probability of x equals to 8 is 5 by 36. Similarly, probability of x equals to 9 equals to 4 by 36. Probability of x equals to 10 equals to 3 by 36. Probability of x equals to 11 is 2 by 36. And probability of x equals to 12 is 1 by 36. Next, we write the required probability distribution in the tabular form as shown here. Now home assignment. Try to solve similar questions of exercise 13.4. Thank you.